So good morning all. Last class, due to some video quality, the session was not so good, but audible you can listen it, and those video I will rectify it and I will share once again. Okay, I will enhance. So last class we have discussed about single tone modulated signal, multi-tone modulated signal, as well as we have seen different spectrums. If it is a modulating single tone modulating signal, if you are going to modulate with respect to carrier, then there are basically three components are available. First is the carrier, second is the lower sideband, and third component is the upper sideband. Okay. Similarly, when we are using the multi-tone signal, more than one number of modulating frequencies available in modulating signal, then the modulated part is divided into certain parts. Okay. Now most important thing is what? Carrier must present as well as some sideband must also present, because in AM this is the important factor that two sidebands and one carrier when one single modulating frequency we are using. But if it is more than one frequency for modulating signal, depend upon that the nature of your sideband going to split. Now as we have derived in the last class that the different spectrums are available, frequency translation what we have done with respect to amplitude, with respect to the frequency. First, carrier will be the center frequency and the upper sideband frequency will be represented in the right hand side, and the lower sideband frequency are going to be represented in a left hand side. Okay. So today we are going to discuss about this modulation index, and that modulation index also we can represent for single tone signal as well as for multi-tone signal. And what are the effect of modulation index while we are transmitting our signal from transmitting end to the receiving end? That effect also we will see. And as well as with the help of modulation index, we can identify the efficiency of transmission. Okay. So efficiency of transmission means our information must be transmitted towards receiver including carrier. So what are the factors will help us to identify, that we will see in today's class. Okay. So first, just I will give a brief of it, what is modulation index. Then we will proceed. So modulation index, as it states that it is a ratio of the maximum amplitude available in modulating signal to the maximum amplitude in carrier component. So this is the modulation index, and as we have seen, if it is less than what happens, if it is greater than what happens, and if it is equals to 1, what happens. If it is less than 1, then we are saying it is called as a under modulation. Okay. If it is greater than 1, then it is called over modulation. Okay. And if it is 1, then it is called critical modulation. In last class we have seen these characteristics of modulated signal changes with respect to these factors. This indicate means the modulating signal amplitude is less than carrier. Then only the envelope will be created without any envelope distortion. Envelope distortion when it will create? When the amplitude of modulating signal is greater than the carrier amplitude. Then only this over modulation will be done. But for practical case, this over modulation we are not using it because it contributes the noise. Because unwanted over envelope distortion will be generated and it will contribute a noise to our transmitted signal. So we are avoiding this over modulation. And that one means it is called critical modulation, or I can say it is called 100% modulation. Okay, 100% modulation. That we will see how it is. Now, this modulation index are the important factor while transmitting a modulated signal from one end to the other end. Okay. Now how this modulation index we are going to represent? Let's see. So let us consider m of t. M of t is equals to Vm cos of 2 pi Fm t. I have considered that message component is a cosine signal whose amplitude is Vm. Similarly, if I am considering the carrier component AC, that is cos 2 pi Fct. So this is the carrier component. Okay, and if I want to determine what is modulation index, so what is the peak value of this modulating signal? Vm divided by AC. Okay, now this I can write k suffix a into Vm. In many of the book, this k suffix a will be discussed. In many of the book, this k suffix a is not discussed directly. They will represent what is modulation index. But this k suffix a is called amplitude sensitivity of a modulator. Okay, this is the frequency sensitivity or amplitude sensitivity. K suffix a is called amplitude sensitivity. When you will deal with the frequency modulation, it will become k suffix f, that is called frequency sensitivity. Similarly, in phase modulation, we can write k suffix p for phase sensitivity. So this k suffix a is equals to 1 by AC. Okay, 1 by AC means unit is volt inverse. Okay, now potential of this modulating signal potential is also represented in volt. So volt into volt inverse, if I will multiply, I will get a constant factor. So that is called modulation index. Modulation index is a constant through which we can decide whether the modulation is done with under modulation, critical modulation or over modulation. If it is done in over modulation, automatically it will contribute the effect of noise, because envelope distortions are going to happen in that particular modulation. Now since this k suffix a is the amplitude sensitivity of a modulator. Now in previous class I have drawn a block diagram that we are feeding the modulating signal to the summation in which the carrier amplitude is added to my modulating signal, then it is mixed with the cos omega ct, and then the AM signal is generated like this. This is the small block diagram for generation of AM signal. Now here this is the system, or this is, I will say it is called as a modulator. Okay, this modulator is having a amplitude sensitivity towards carrier. Okay, so that amplitude sensitivity towards carrier is k suffix a, which is equals to 1 by AC. So this is my modulating signal, this is my carrier signal, this is the modulation index. Now we will represent this modulation index in represent AM signal in terms of modulation index. How? Let's see. So now I am writing a general expression for modulated signal, AM signal. So how we can write? It is A suffix c plus m of t and cos omega or cos 2 pi fc. Done. Now here whatever I am doing, it is only with respect to one modulating signal whose frequency is FM. Okay, whose frequency is FM. So here I will write it is single tone. It is a single tone. Single tone modulated signal we are generating. So single tone modulated signal means it is having, modulating signal is having only one frequency component. And the consideration is what? The consideration is your modulating signal frequency is very less than carrier frequency. then only the carrier will carry that frequency to a longer distance. Okay. Now if I am going to expand this, so if I am going to expand this, I will get AC cos 2 pi FCT plus there are two sideband's are available. One is lower sideband, one is upper sideband. So here, if I am going to expand this, I will get Vm by 2 cos of 2 pi Fc minus Fm of t. This is the lower sideband, and another one Vm by 2 cos of 2 pi Fc plus Fm of t. So this is the upper sideband. So single tone modulated signal consists of carrier, consists of lower sideband, and consists of upper sideband. Done? Now I need to represent this equation in terms of modulation index. How we are going to represent in modulation index? As we know that modulation index is a ratio of magnitude of modulating signal to the carrier component. So in place of Vm, I will substitute Ma into AC. So here I will write it is AC cos 2 pi FCT carrier component plus in place of Vm, I will write M suffix A into C divided by 2 cos of 2 pi Fc minus Fm of t plus Ma into A divided by 2 cos of 2 pi Fc plus Fm into t. Okay. So this is the carrier representation, because since it is an AM signal, carrier must be there. So this is my carrier signal. And these are the two sideband. This is our lower sideband and this is our upper sideband, whose amplitude is Ma into AC by 2. If you substitute Ma, that is Vm by AC, you will get in terms of Vm. Okay, because in place of Ma, if I will substitute Vm by AC will be cancelled out. Vm we can represent. Done. So with respect to this Ma and Vm can also be written. So in place of Ma, you can write K into Vm also. Okay. So this is the representation of amplitude modulated signal for single tone represented in modulation index. So this is my modulation index into AC divided by 2. Now how I will represent in frequency spectrum? Very simple. So first, this is the center frequency, that is Fc. This is S suffix Am of F, and this is your F. This is the amplitude. So what is the amplitude available in this spectrum? It is AC by 2. Because last class we have discussed why it is AC by 2. AC by 2 means if you expand this one in terms of impulse function, it will become AC by 2 del of F plus Fc plus del of F minus Fc. Okay. So only positive side I am considering, whose strength is AC by 2. So this is Fc. Next, to represent the upper sideband, that is Fc plus Fm, and what is the amplitude? Amplitude is Ma into AC divided by 2. Similarly, lower sideband, it is Fc minus Fm, and amplitude is Ma into A divided by 2. So this is the right hand part. Left hand side also you can represent, that is the reflection part. But for the time being, I am discussing only the right hand side part. I am not discussing the mirror part. So this is the frequency translation for single tone modulated signal in terms of modulation index. Okay. Next we will discuss about the multi-tone modulated signal. Okay. So now we will discuss about multi-tone signals. Means here I am going to use a modulating signal consists of more than one number of frequency, more than one number of low frequency. Okay. So let us consider message signal m of t is equals to Vm1 cos of 2 pi Fm1t plus Vm2 cos of 2 pi Fm2 of t. Okay. Now modulating signal is having two different frequencies. What are the two different frequencies? Fm1, which is less than Fm2. So we have considered that this modulating frequency is greater with respect to Fm1. And one more important thing I will tell later on about the transmission bandwidth. First we will discuss this, then we will write all those transmission bandwidth. So Fm1 is less than Fm2. Now for this case, if I am going to write the AM signal like I have written in single tone. For single tone there are three factors are available. One is the carrier and two are the sideband. But here there are two modulating signals are available, means one will be carrier, two sideband correspond to the frequency F1 and two sideband correspond to the frequency F2. So how we are going to write? Let's see. So S suffix AM of t is equals to first AC plus M of t whole into cos of 2 pi FCT. So this is the general equation for an AM. Now what I will do, I will substitute this value here. So first is my carrier. First is my carrier cos of 2 pi FCT. Done. Plus sideband corresponding to this one we will write. How we will write? It is Vm by 2 cos of 2 pi Fc minus Fm1 into t plus Vm1 divided by 2 cos of 2 pi Fc plus Fm1 of t. So these are the two sidebands corresponding to the modulating frequency F1. This is called lower sideband and this is the upper sideband corresponding to this frequency component. Next, this is another information is available. So plus Vm2 divided by 2 cos of 2 pi Fc minus Fm2 into t plus Vm2 divided by 2 cos of 2 pi Fc plus Fm2 into t. So this is the whole equation for multi-tone signal. So first is our carrier. Okay. Second, these two factors are the lower sideband and upper sideband corresponding to the frequency F1. Then these two are the factors are the lower sideband. Here I will write LSB2, here I will write LSB1. This is your USB1 and this is your USB2. Okay. So these are the sidebands. So that means if there are two frequencies are available, two modulating frequencies are available, then in spectral analysis in this there will be 5 spectrums are available. Center frequency will be our carrier. Right hand side two spectrums will be there, one with respect to the first modulating signal and one with respect to the second modulating signal. Okay. So that also I will draw for you, so that you can analyze all these things in a clear manner, because this thing I have discussed in the last video but not so clear wise. So I'll represent once again. I am drawing only the right hand side part, not to the left hand side. So it is AM of F and this is F. Okay. Now first, this is my center frequency. Okay. Center frequency is FC. Now what is the amplitude of FC? Amplitude of FC or amplitude of a carrier is AC by 2. Next, this is one sideband and this is one sideband corresponding to the frequency FM1. So here I will write FC minus FC plus FM1 and here I will write FC minus FM1. Okay. Next, another spectrum is available. What is the spectrum? FC plus FM2 and here one more spectrum FC minus FM2. So there are two upper sideband spectrums are there and two lower sideband spectrums are available. Okay. And one more important thing, what is the amplitude? Now here you can see it is Vn1 by 2. Here it is Vn2 by 2. You can write this whole thing in terms of modulation index also. How I can write? M1 into AC divided by 2. M2 into AC divided by 2. Here I will write M1 into AC divided by 2. Here it is M2 AC divided by 2. Now what is M1, what is M2? M1 is equals to Vm1 by AC. What is M2? It is Vm2 by AC. Okay? Same thing I have written there. Here you can write Vm1 by 2. In place of Vm1, you can substitute M1 into AC. M1 is the modulation index corresponding to the Vm1. And M2 is the modulation index corresponding to the second component. Okay. Now there are two things will come into picture. Now if there are two different modulation index are there, what will be the net modulation index for this AM signal, for this multi-tone AM signal? So for that, in last class I have given a formula that net modulation index MA, net modulation index MA. So MA is equals to root over of M1 square plus M2 square. Why it is M1 M2? Because there are two different modulating frequencies are there. But if it is more than one number of modulating frequencies are there, then means the general expression will be M1 square plus M2 square dot. This is the general representation. But for this case, we have considered two different modulating frequency. Here, MA will be M1 square plus M2 square. Okay, this is the first one. Case 1 regarding the modulation index. Case 2. Case 2 means it will discuss about the bandwidth. And this bandwidth is called as transmission bandwidth. It is also called as transmission bandwidth, BW. Transmission bandwidth. So when I am going to transmit this multi-tone signal, what will be its bandwidth? So what I will write? Bandwidth is equals to twice of Fmax. Okay. So what is Fmax? Fmax means the maximum frequency available in the modulating signal. As we have considered that FM2 is greater than F1, that means my bandwidth will become twice of FM2. Okay. This is theoretical calculation, but spectral analysis also